Hello everyone, today's video is submitted by a viewer, and it says, the curve C1 has parametric equations x equals t squared, y equals t cubed, where t is a real number. Let O denote the point 0, 0. The points P and Q on C1 are such that the angle POQ is a right angle. Show that the tangents to C1 at P and the tangents to C1 at P and Q intersect on the curve C2 with equation 4y squared equals 3x minus 1. Determine whether the curves C1 and C2 meet and sketch the two curves on the same axis. Okay, so interesting. I'm not sure. I mean, there's going to be a lot of algebra involved here. I don't know exactly what these curves look like. But so C1 is parameterized by x is equal to t squared and y is equal to t cubed. So as t ranges over the reals, x goes something like this, back and forth, and y I mean, we'll have something like this, and in fact, I suppose it'll be a cubic, what do we have here? We have y is equal to x to the power of 3 over 2. So what does that look like? Something like that. And we also get to have this negative part. So I'll put this in parentheses because, you know, for positive values of t, the curve looks like that. For negative values of t, the curve looks like that. Okay. So we have the origin, of course, and there are points P and Q on this curve such that they form a right angle at the origin. Now what that means is one point is going to have to be in this quadrant, either P or Q, and the other point will have to be in this quadrant. Because, you know, if I choose any 2 points in this quadrant, they cannot form a right angle with the origin. So the first thing we need to do, hold on. What do I want to do here first? Let's say for the point P, we have TP, and for the point Q, we have TQ. So then XP is TP squared, and YP is TP cubed. Similarly, XQ is TQ squared, and YQ is TQ cubed. And I suppose we could think of these as vectors. P is XP, YP, and Q is XQ, YQ. And if these form a right angle, then the dot product is 0. So then let's suppose we're going to say that TP is greater than 0 and TQ is less than 0. So Q is in the bottom right quadrant. I also have XP, XQ plus YP, YQ is equal to 0 because of the right angle. So I have TP squared, TQ squared plus TP cubed, TQ cubed is equal to 0. So this says that 1 is equal to 1 plus TP TQ is equal to 0. So TP is equal to -1 over TQ. Okay, that will be useful, I'm sure. because this tells us all of the pairs of points that satisfy this right angle condition. Okay, so that's the relationship between the two values of t. If I trace out what the curve looks like, something like this. If I have some value of t, which gives me the point Q, then I can easily compute the corresponding value of t up here, which gives me the point P. They're just reciprocals, negative reciprocals. Then, the first step of what the question is really asking is first we compute tangents here and here. Those tangent lines are going to meet somewhere. And we have to find, I suppose, a parametric equation for the curve where these tangents meet. Oh my. Okay, I'm gonna write everything in terms of TP. TP is like my proper variable. So first, maybe there's some kind of shortcut, some kind of clever relation or something like that, but what I'm going to do, I'm going to find the equation for this tangent line, and I'm also going to find the equation for that tangent line, and I'm going to find the point of intersection of those two lines. And that should be written in terms of TP. So tangent at P. Okay, well, I'm just going to call TP, I'm going to call that T. So I have the point t squared t cubed, and the derivative of my curve at that point is just 2t and 3t squared. Wait, hold on. How do you do this parametric derivative stuff again? So I'm going to think of well, first, the direction vector is 2t, 3t squared. So then the line going through that point is given by t squared t cubed plus k times 2t 3t squared. So this is a vector representation of the tangent line. Okay. And k is a parameter. So we're thinking of t as being fixed. T is being fixed at such that it corresponds to the point P, and this gives us a vector representation of a tangent line. So now for the point Q, I have the point Q is equal to 1 over t squared and negative 1 over t cubed. And is it best to still think about this in terms of derivatives of with respect to t? I guess it doesn't end up making any difference. So the direction vector of the tangent line here is going to be negative 1 over negative 2 over t cubed, and 3 over t to the 4. So the vector representation for the tangent line to Q is 1 over t squared and negative 1 over t cubed plus some other constant times negative 2 over t cubed, 3 over t to the 4. C is again any real number. And what I want are the values of k and c such that these two lines intersect. So I have t squared plus 2kt has to be equal to 1 over t squared minus 2c over t cubed. And I have t cubed plus 3k t squared is equal to negative 1 over t cubed plus 3c over t to the 4. Now t is fixed everywhere. I want to think of this as an equation, system of equations for k and c. So this is a system of equations for k and c. Once I find k and c, that will give me the point where these two lines intersect. This looks pretty messy, but let's see if we can figure it out. I'm going to simplify first. Okay, so let's multiply the top by 3 and the bottom by 2. Oops. And add them together. So 6 t to the 4 plus t squared k is equal to 3t plus t minus 3t to the 5 minus 2t minus 2t to the 7. This is a mess. So that's the value of k, and now I can just substitute k into this equation to get the point corresponding to the intersection. Okay, well, the point of intersection, we'll call it I, is equal to t squared comma t cubed plus 2kt comma 3k t squared. Man, this is so messy. Hold on, there's something simplifies here. That becomes just a single t. And I suppose we can cancel some t's here. This stuff is supposed to simplify here. T squared plus, if I multiply k by 2, that becomes a 3, and this t will cancel stuff there. So I guess 1 minus 3t to the 4 minus 2t to the 6 divided by 3t squared plus 1. And the other parameter is t cubed plus, so if I multiply by 3k, if I multiply k by 3t squared, that becomes a 2. I'll cancel 1 power of t there and add 1 power of t to the top. Maybe some stuff simplifies. Okay, so 3t squared plus 1 times t squared I mean, I don't know. I'm just doing algebra here. What is like? So this is some parametrized curve, which tells us where these tangent things intersect. I mean, there's got to be a better way to do this, but I don't see what it is. And as long as I didn't make any arithmetic mistakes or algebra mistakes, that's correct. Oh, of course, sorry. We're not just trying to find that curve. We're trying to show that it's parametrized. We're trying to show that it has an equation 4y squared equals 3x minus 1. Okay. maybe that's doable from what I have. I mean, I've gone through a terribly messy way of doing that. But if I can show that if I take this, square it, multiply by 4, that's the same as taking this, multiplying by 3, and subtracting 1. Oh, Lordy. Let's maybe go back to, I have the points t squared and t cubed, and 1 over t squared, negative 1 over t cubed. So this is my parameterization of pairs of points which create right angles with the origin. How about I do it like this? I have the vector equation for one of the tangent lines. This, again, t is fixed. Now let's fix, this is for TP fixed. If I fix TQ, That's the vector equation again. If I want these to be equal, this has to equal tq squared plus 2 tqc. Okay. Oh, I need to multiply the top by 3 and the bottom by 2. And now add together 6 TP TQ plus TP squared, okay, is equal to 5 TQ cubed minus 3 TP squared TQ minus 2 TP cubed. Essentially the same thing we had before. We're just, because we know that the relationship between TP and TQ is their reciprocals. Do I have a sign mistake somewhere? This looks different than what I had before. So I'm making an arithmetic mistake somewhere. Oh my goodness. Okay, I made mistakes. I made mistakes here with something. I think I'm going to assume that what I have here is correct. So then the point of intersection, it was incorrect what I had above. It's going to be t squared plus 2kt t cubed plus 3t squared k. Okay, a little bit simpler than before, more simplified expression, but here's my parameterized curve of the intersections. And I need to show that 4 times that squared is equal to 3 times that minus 1. So we'll call this xt, call that yt. So yt squared is equal to 1 minus 2 t to the 4 plus t to the 8 divided by 4 t cubed plus t squared. So 4 yt squared is equal to 1 minus 2 t to the 4 plus t to the 8 divided by t cubed plus t squared. And 3xt minus 1 is equal to t to the 6 plus 1 over t to the 4 plus t squared, like that. T to the 6 minus t to the 4 minus t squared plus 1 divided by t to the 4 plus t squared. These don't look equal, but Oh. Let's keep this as 1 minus t to the 4 all squared divided by t squared times t squared plus 1. This is 1 minus t squared 1 plus t squared times 1 minus t squared 1 plus t squared divided by t squared plus 1. I don't get that they're equal. Oh wait, no I do. That was supposed to be squared here. Squared. Okay, yes. So I have that 4 yt squared is equal to 3xt minus 1. Determine whether C1 and C2 meet. Well, C1 is basically, like I said earlier, y is equal to x 3 over 2 and y is equal to negative x to the 3 over 2. And this is a parabola opening in which direction? Opening to the right. Let's write this as 3x is equal to 4y squared plus 1. So maybe they don't intersect. So the original curve is something like that. It's not quadratic, but it's more than linear. When y is equal to 0, x is equal to 1 over 3. And it's opening in this direction. How can we determine whether these curves intersect? Well, if these curves intersect, then there's some value of t where 3t squared is equal to 4 times t to the 6 plus 1. Um, so if and of course we can restrict ourselves to positive values of t because of that symmetry we had earlier. So when t is equal to 0, the left-hand side is positive. If I take a derivative, I have 24 t to the 5 minus 6t. When is this positive? When 4 t to the 4 is greater than 1. So this is negative. Negative when t to the 4 is less than 1. Less than 1 over 4. Let t be equal to 1 over 4 to the power of 1 over 4. 4 t to the 6 minus 3 t squared plus 1 is then equal to 4 1 over 4 to the power of 3 over 2 minus 3 1 over 4 to the power of half plus 1. Okay, so we have 4 times 1 over 2 cubed minus 3 times 1 over 2 plus 1. So this is 4 over 8 minus 3 over 2 plus 1. Let's simplify this. So this is equal to 0. Okay, so what does that say? It's saying that this starts when t is equal to 0, this is equal to 1. When t is equal to this number, this thing is equal to 0. So they do intersect, and they intersect when t is equal to plus or minus that number. Man, I think I did that right. So in fact, I guess that means they must intersect. They intersect tangentially, because one of them curves this way, and the other is curving that way. If they ever crossed somewhere, they would cross again. I'm not going to sketch them precisely, but yeah, they do meet. Yeah, I mean, this question ended up being extremely tedious. I liked it originally, kind of like another question submitted recently. The key here is right at the beginning. If these points P and Q make a right angle with the origin, then this dot product is 0, and you can solve for the two values of t, or the relationship between them. The rest of it was just messy algebra without really any inspiration needed, I guess. Yeah, I don't think I have much more to say about this one. Thanks for watching.